This is a short tutorial on empirical formulas and molecular formulas and the associated calculations. So let's start by defining what an empirical formula is. It's the smallest whole number ratio of atoms present in the compound. That may or may not be equal to the literal number of atoms in the compound. The molecular formula are the actual numbers of each atom present in a molecule of the compound, or formula unit if it's ionic. Now we can determine that the empirical molecular formula of the compound based on either the percent composition of each element or the mass of each element in the compound. And generally both of those are experimentally determined. Let's look at a few examples of that. We take hydrogen peroxide there. We can see that we can pull a factor of 2 out of that and get HO. So H2O2 is the molecular formula, where HO is the empirical. We take benzene, C6H6 versus CH. I pull a factor of 6 out of there from the molecular to the empirical. In the case of water, what we see is that the empirical and molecular formula are the same. There's no factor to pull out, which is also the case in most ionic compounds, because the way we define that formula is the smallest whole number ratio that produces a net neutral compound. So to calculate an empirical formula, we're going to start with the number of grams of each element given in the problem. In some cases, you're given percentages. If you are, just assume a 100-gram sample so that the mass of each element equals the percentage given. That's just making the math easy. You could technically pick any size sample you wanted. Then in either case, we're going to convert the grams of each element to moles using the molar mass of each element from the periodic table. And then whichever one of those moles is the smallest, we're going to divide that into each of the moles and get what I call a mole ratio. That mole ratio then is rounded to the nearest whole number, and that will then be the subscript in the empirical formula. In some cases, you don't quite get a whole number to where you could round off, so there might be some factor to get the lowest whole number possible. Most commonly, if you have a 2 to 3 or 2 to 5 proportion, you'll get a half in there, indicating that odd proportion. And then, say, for example, you get 1.5, you'll have to multiply each of those by 2 to get 3. Not just the 1.5, but all of the mole ratios. So, for example, if we have a compound between tin and chlorine, where the mass of the compound is 2.571 grams and is found to contain 1.171 grams of tin, watch the empirical formula. First off, I need the mass of the chlorine. So 2.571 grams minus 1.171 grams is 1.4 grams of chlorine. Now I have the mass of both elements. Now I can divide through by the molar masses to get moles. Chlorine divided by 35.45, molar mass of chlorine, and I will get 0.03949 moles of chlorine. Do that for the tin. Divide by 118.69 grams of tin per 1 mole, which is the molar mass off the periodic chart, and I get 0.009866 moles of tin. Divide both those by the smallest, which is the moles of tin. So we're going to divide them both by 0.009866 moles. I get 1 for the tin and approximately 4 for the chlorine. Those are going to be used as subscripts in my formula. So I get the empirical formula being SnCl4. Here's another example, except it involves percentages this time. So we've got a compound between aluminum and oxygen found to contain 52.9% aluminum and 47.1% oxygen. What's the empirical formula? So we're going to assume our 100-gram sample, which means I'm just going to take the percent sign off and stick grams in. So that makes our math easier, assuming that 100-gram sample. From that, we're just going to work the problem normally. Divide through by 26.98 the molar mass of aluminum, and I get 1.96 moles of aluminum. Take the 47.1 grams of oxygen, divide through by 16 grams per mole, and we get 2.94 moles of oxygen. There's an approximately 2 to 3 proportion there, but let's go ahead and divide it out. So we divide through both of them by 1.96 moles. And so I get 1 aluminum to 1.5 oxygens. So I'm going to multiply 3 by 2. And so we get 2 to 3. 2 aluminums to 3 oxygens. So we can say our empirical formula is Al2O3. So if we look at this example, we have mesostyrene, which occurs in small amounts in crude oil, and has an empirical formula C3H4. And if we know the compound has a molar mass of 120, essentially, grams per mole, what is the molecular formula? First thing we need to do is add up the molar mass of the C3H4 unit, and then that's going to tell us how many of those go into the molar mass. So our molar mass, we got 3 carbons at 12.01 grams per mole and 4 hydrogens at 1.01 grams per mole. Adding that together, we get 40.07 grams per mole. And we want to see how many times that goes into our molar mass. Dividing it out, we get essentially 3, because 120 divided by 40 is 3. So what that ultimately means is we're going to multiply our formula C3H4. All the subscripts get multiplied through by that factor of 3. And when we do that, we find out we get C9H12, because that's 3 times 3 is 9, and 4 times 3 is 12. Now in this case, I give you percentages again, but I give you also the molar mass. If you have the empirical data and you have the molar mass, you can calculate the molecular formula directly without going through the empirical. The trick is you assume a molar mass size sample instead of 100 grams. So let's try that. So in this case, I'm going to assume 50-50 split on the percentage. So I'm going to say 50% of 128 is 64. So we'll change both of those to 64 grams of sulfur, 64 grams of oxygen. And now let's proceed normally. Divide through about 32.06 grams per mole. And then we get about 2 moles of sulfur. Do the same for the oxygen. We're going to divide through by 16 grams per mole. Get 4 moles. So you can see I got a 2 to 4 relationship. And since I used the molar mass as my size sample, those are the subscripts on my empirical formula. So I can say the molecular formula is S2O4, and I can pull that factor of 2 out and say the empirical formula is SO2. So in this case, the 2 and the 4 are the subscripts on my molecular formula to calculate directly. I could work this problem the other way and get the empirical first and then scale it up like I showed you before. This way is just a little faster. So this has been a short tutorial on empirical formulas.